Hello and welcome everyone. This is the Ethereum Engineering Group meetup recording of the decentralized random number generation that we did yesterday. Unfortunately, the live stream didn't work, so I just thought I'd introduce the topic because the normal introductory piece is missing from the recording. So I did the talk, and I've had a lot of people give me some feedback and also provide some helpful links and ideas, and they're noted on the one of the early slides. I think I skate over that a bit. One other question that was asked that didn't end up on the recording was, how does my scheme relate to Justin Drake's scheme? So they're covered late in the recording. And so Justin's requires less communications. So his one is just n squared, whereas my one was 3n squared. However, if you were doing on-chain verification, I've perceived that my scheme may end up using less gas. Though obviously we need to actually create a POC to really test that out. And maybe there's a scheme which is halfway between the two, which is both has less communication and uses less gas. So anyway, I guess that's something that can be done at a later date. So anyway, please enjoy the presentation.
All right, so I'm just going to wind back very quickly. All right, for the recording, decentralized random number generation. I thank those people down the bottom there. All right. Now, so what do you want to actually use this for? You know, why would you do decentralized random number generation? Well, if you're going to do, say, a lottery. In fact, there's a really great video that I've seen where back in the 80s there was a live lottery on TV, and by mistake the people who were cheating, the numbers actually came up on the screen before the balls had been dug out. You know how they've got the balls in their thing and it's going, and then they actually appeared on the screen just parts of a second before the balls actually popped out of the machine. Apparently, I think it was Vlatter, anyway, the guy who was involved in soccer, apparently they heated up some of the balls, so he put his hand in to pick out the ball which would say, hey, this country has won the rights to host the Soccer World Cup. And so one of the balls was heated, or something along those lines, so he could just go in and find the correct ball, as it were, in this blind lottery. So, and I've taken those two from some kind gentleman who lives in, was presenting at Stanford University. So those two examples are from someone else. But what great ideas, here you are, you're doing something public that's supposed to be very random, and yet, golly, people cheat. So you really do want to have try and do something that people can't cheat at. And it could also be, like in the blockchain world, can be who gets to generate the next block and hence get those block rewards. So in proof of work, it's chosen by who finds the best hash, but in something like proof of stake, you've got to have a way of allocating who's actually going to be the miner of the next block or the minter of the next block. So there are a couple of properties that would be really desirable to have when you've got a decentralized random number generator. So you want to have it available. So in other words, you can, even if you've got malicious nodes, you can successfully complete the algorithm. And so you often in blockchain systems you hear about liveliness and safety. So this is as an equivalent to the liveliness property. So we want, say, Ethereum, no matter what happens, to keep on going. In fact, there's a quote from someone saying, even if you have World War III and 90% of the nodes are knocked out, you still want Ethereum to keep on cruising along. And so that's liveliness. It's going to produce the next block. Unpredictability means that if you're some actor in the system, there's no way of you understanding what the output will be or could be ahead of time. And unbiased is sort of related to that, but it's a bit stronger. It says there's no way of influencing the output. So why that might be useful is, imagine if imagine if Rob Coote and I were going to do a coin flip thing, and I said, all right, well, we'll flip the coin twice, and if we get 2 heads, then something will happen, and maybe some money will exchange. So at the moment that's 25% probability, but if I could influence the first bit to be, say, 0 and not 1, then suddenly it's gone to 50-50. So I'm entering the whole thing thinking 50-50, he's thinking it's 25-75. So that's what influencing is all about directing it so the probability of things happening isn't what you'd expect. Verifiability is about being able to prove that the random number generation process was correct, and so a third party can verify it. Not every algorithm needs to have that public verifiability. You could have nodes in a network, and as long as all the nodes themselves feel happy with the algorithm, then you don't need that public verification. Scalability, so you can have thousands or many participants in the algorithm, and so how does it scale? And quantum resistant, so if quantum cryptanalysis becomes reality, will this algorithm still be solid and secure? There's also the idea of the last actor, and so the last actor problem is common to many schemes, and so the idea is that you'll have n participants in the scheme, and if you can just sit around and wait for the first n-1 participants to participate, then maybe you can do something to either generate an output of your choosing, or maybe bias the output in some way, or maybe help the algorithm. So the last actor is a common fault in these algorithms, and so something to think through. So the first algorithm I'm going to talk about is a very basic and naive XOR scheme. So this is pretty much as simple as you could do it. So you have n participants, and everyone generates a random number, and then everyone posts their random number, and then you use XORs. XORs a mathematical thing, so if you have 0 XOR 0, you get 0, 1 XOR 0, you get 1, 0 XOR 1, you get 1, 1 XOR 1, you get 0. So if the numbers are the same, you get 0, otherwise if they're different, you get 1. And so essentially it's a way of combining all of these numbers together to give you the random output. So that's a very simple way. But if you're an attacker and you're the last actor, then what you can do is you can wait for everyone else to put in their values, and then you can say, well, I want this certain desired value, and then you can calculate the random number you need to have, and if you submit that random number, then you will get the desired output. So as a last actor, you've been able to actually produce the output you desired. So obviously that's not very good. So that means that this algorithm actually fails at everything, except it is quantum resistant, so that's good. So another simple scheme is commit reveal. And so in the early days of proof of stake, this was the scheme that was being proposed. And so the idea is you have n participants, and everyone calculates the message digest of their random number. They call it C, so commitment. And then you post your commitments, and then once all the commitments have been posted, then everyone reveals their random number, so commit reveal. And then you calculate the random output as the combination of all the input values. So if you're an attacker, and you're the last actor, you watch all of those other ones come by, so R0 to Rn-2, and then you look at the output, and you say, well, do I prefer that output value, or the output value that you would have if I put my value in? You've suddenly got a choice, and you're the only one with that choice. No one else has got that choice because everyone else has already put in their real value. So, so if you require all of the participants to participate, then you could halt the algorithm. So if you don't want to halt the algorithm by not contributing, then what you could do is you could say, well, look, if you don't contribute your random number after committing it, we'll fine you. So, you hear about slashing in these algorithms, so we'll slash you. You could do that, but then what happens if the reward I get is greater than the fine? So maybe there's some bet, maybe, we were talking about Rob Coote and I doing some bet, and if I can work out that suddenly I'm more likely to get, I don't know, $1 million, then if I get fined $20,000 or something, it's nothing. So you've got to think about what the rewards are versus the fine. So it's available, assuming that you proceed with the algorithm, even if some people who've committed don't reveal. And it is unpredictable. So you can't actually predict the output, but you can influence it halfway through. So it's unpredictable but not unbiased. But it is quantum resistant. So the next technique, this is actually the ones that is being proposed by Ethereum Foundation for Ethereum 2.0. So there's this idea of a hash onion. So you can think of, in an onion, you've got many layers. And so in the middle, you could have your secret in there. And so what you do is you do the hash of the secret, gives you the output. That output is then hashed to give a secondary output, and then you hash that. So you keep on hashing. So you can think of commitment 0 is the hash of commitment 1, commitment 1 is the hash of commitment 2, and then commitment n-1 is the actual hash of the secret. So it's by successive hashing is this idea of the hash onion. And so the idea is that you could post a commitment, this C0 value, and then next, when you post C1, what you're doing is, those two values are linked together by that cryptographic hash. So you can't change the value C1 that you reveal. And because once you've revealed C1, then the next time you go to reveal, you must reveal C2. You can't, because there's no way of changing the cryptographic hash. So you're essentially, by locking in that commitment, C0, you're locking in a stream of commitments. So if you had 1 million hashes here, then you would have 1 million random or million commitment values that are all interlinked by cryptographic hashes. And so observers can check that you have revealed the right values by just looking at, all right, well, last time you revealed C0, now you've revealed C1. Does the hash of C1 equal C0? Does the hash of C2 equal C1? So you can verify whether someone's done the right thing. And so once you've committed to C0, you can't change the sequence. So RANDAO, I assume that's how you say it, though anyone's allowed to correct me if they want to pronounce it in a different way. So this is the mechanism that Ethereum 2 is running with. And so you have I validators that you have in the overall group. And C0 VI, so the initial commitment value for each of the validators is put somewhere that everyone can see. So you could imagine it could be in a smart contract, but it's not going to be. It's going to be in some shared store. And then what happens is that you've got an initial random number value. Let's not worry about where we get the initial one from. And you say, well, the h to the -1, so essentially give me the pre-image of that. So in other words, where we had, if it's C0, the pre-image of C0 was C1, wasn't it? So you say, for this validator, VI, give me the pre-image of what we're up to. And then we'll XOR it with the old random number, and we'll get the new random number. So how we can think about it is, say Grant's a validator and I'm a validator. So I've revealed up to, say, C2 for my validator, and he's revealed up to say C3 for his validator. So I XOR it in, and then the new random value says, all right, it's over. Yes?
Sorry, Peter, what's the preimage? How's that calculated?
A preimage of a hash, so the preimage is essentially the value that you're hashing. So the image is the actual hash value, and the preimage is the value that you hash.
Okay, thank you.
Yep. Okay. Yeah. So going on with our example. So Grant's up to say, so the random number that I produce is such that it chooses Grant as the next person or next entity participant to partake in the algorithm. And so then you reveal your next commitment value and XOR it in with the random value. And then maybe it then goes from you to Mark. And then Mark is up to, say, his first commitment value, and then he reveals his second commitment value. And so each of us participants have got different commitment values that we're up to. So we each are rolling back. And so this is a way that you're only actually doing one calculation for the whole network, rather than, those other ones, the calculations being happening all over the place. Whilst this one, there's only one calculation happening for the whole network, and everyone can verify it, because you can look at the as we unroll this hash here, and unroll the commitments to make sure that I haven't cheated with my commitment, Grant hasn't cheated, nor has Mark. But what happens if if one of the validators doesn't reveal their commitment value? Well, in that case, have a look at those Ethereum research articles there for big long discussions about probabilities of people doing it or not doing it. So it has pretty good availability. I think there is a great incentive for people to reveal. It is unpredictable because you're not going to be able to work out the output. And I've written unbiased in red here, though Ben, in some discussions, said that actually there's a way that they've hardened the algorithm. And I think, essentially you've got to look at some of the links that were provided in the previous slide to work out exactly why. So that's maybe brown, halfway between red and green. And it's verifiable. You can verify the numbers. And I think it's pretty scalable, and it's quantum resistant. So it's actually pretty good. So another thing that you've probably heard a lot about are verifiable delay functions. And so the idea is that you want to have an algorithm which you can run serially, but you can't run in parallel. And the idea is it takes a long time to calculate, but only a short time to verify. So if you can think of, say, RSA private key operations and public key operations, that's a good example of the same sort of thing. It's very quick to do public key, slower to do private key. Similar sort of thing. The example I've got here, though, is it's pretty difficult and slow to do, say, a square root. So working out the square root of 49, coming up with 7, you might go down the algorithm that's just over to the right there. And exercise for later, have a go, it works. So that'll give you the square root. Whereas you can imagine multiplying two numbers together gives you a result, and that's pretty quick. And so you can see you've got an asymmetric timing algorithm. And so the goal is that you want to have the calculation versus verified be 100 times different. And you could even perhaps chain multiple of these VDFs together as well. That's another possibility. So the algorithm that's actually being run with does involve square root, but it's actually a modular exponentiation sort of thing, where you're modularly exponentiating to a square root sort of thing, or a root mod n. And so Ethereum Foundation are actually working with chip manufacturers, because the idea is that you want to run this algorithm as quickly as physically possible. And so the thought is that if they find some hardware that's pretty good and commodity chips, then even an attacker that invests significantly won't be able to get too much of a speed up such that it would break the algorithm. So that's the general theory of that. And there's the actual algorithm being used is in that paper there. And so Ethereum Foundation are proposing actually to use the two together. So, so the RANDAO, so you can imagine you've ended up with that possibly biased, but pretty rock solid random number out of a RANDAO algorithm, and then you put it into a VDF. And so the idea is that you have a delay between when you put it in and when it comes out. So then you're not going to be able to work out what the outcome is going to be because it's physical. It's going to take a physical amount of wall clock time. And so the idea is that you can't try and bias it because you won't know if you won't know if you commit or don't commit, what that will do because you don't know the output yet. And because it would be based on the number that's produced each time, then it's hard to work out ahead of time. So the theory is that it should be solider. Obviously, one of the concerns is that someone will work out a faster algorithm for working out the particular modular exponentiation root mod n thing. So the VDF with RANDAO, it seems that it would be available, which is good because anyone, once they've got that number out of RANDAO, could run the same algorithm using the VDF chips. And in fact, you could run it even on your desktop computer. It's just going to take a lot longer to run. It would be unpredictable and unbiased, and you could verify it, and it should be scalable because anyone should be able to run the algorithm. Quantum resistant, you'll notice that's in a darker shade of green, and that's because all this modular exponentiation stuff isn't actually quantum resistant. However, if you did have a quantum cryptanalysis attack on it, what that would do is it would fall back to the RANDAO itself. So the weakest the security could get will be the security of the RANDAO algorithm because it's one chained onto the other. Okay, so I'll just have a sip. So the other schemes involve secret sharing, essentially. And so to understand secret sharing, it's good to, as a starting point, think about polynomials. So an equation that's order 2 can be defined by 3 points. So this is what? Y equals x squared plus 3x minus 3. So if we've got any 3 of these points, then we can recreate the curve. High school maths. And, we could even have 2 equations. And the interesting thing to think about is, though, that you can add equations. So you can add these 2 equations to give that third equation. But also, you could add the individual points. So if you look at x equals 1, you could add y equals 1 to y equals 23 to give you y equals 24. And for x equals 2, you could add y equals 7 to y equals 22 to give y equals 29. And so not only can you add the equations, but for each individual point on the x range, you can add the y values to give you the y value for the other equation. So, that's quite powerful. So Shamir came up, so this is like the SNRSA guy. So he came up with a split secret algorithm where you've got n shares, and you want to be able to recreate it using m of n shares, and you don't want to reveal any information about the secret if you've got less than n shares. There's a link to his paper. And so the idea is you define an equation, which is similar to the equations that we've just seen. Big thing is, though, that we do it modular a prime field. And P is big, like 2 to the 256, 2 to the 1024, something like that. And if x equals 0, then all of this, yx, so y, will equal a0. So in other words, a0 is the y-intercept, so where the equation hits the y-axis. And so m is the threshold number of, the threshold number of shares that you need to recreate the curve. And so you randomly generate a0 to am minus 1, and they've got to be in the range 1 to p minus 1. And then you securely distribute your shares, and then any m of those shares can be used to recreate the equation, which can give you the x equals 0 value, which is a0. So that maths can be used in things like this. So there was a guy called Feldman who came up with a verifiable secret sharing scheme. And the idea is that you have a generator, and then they deal out essentially random polynomial, and then they publish. So we had this equation, which is very much similar to the Shamir equation, and then they publish these values fi, which is g to the ai, and then secretly they give out the x values for that equation. And so they've published these essentially commitments to the coefficients. And then what you can do is, because you know that you can do the product of fi x to the I, so essentially if you can think of it's a way of doing multiplication and addition using exponentiation. Anyway, so it's a way of publishing values, and then you can check that the x value that you've been shared is correct or not, because you can go g to the and then feed it into this equation here. So that's a way of verifiably doing secret sharing. So Pedersen decided, well, what we could do is we could do a distributed key generation scheme. So rather than there being one dealer, what you can do is everyone is a dealer. So everyone comes up with their own equation, everyone shares that commitment equation publicly, and then what you can do is, each party then, because they can detect whether an invalid value has been published, they could complain if it's invalid, and then if enough parties complain, then a party is essentially struck off, and they're not part of the qualified list. And then each one who's part of the qualified list publishes their y values, and then you calculate the equations, and then for the x equals 0, that should be x there, for the x equals 0 value, you can then sum all of the y values. And so when you're summing all these y values, so essentially the a0 value for all the equations, then that is your random number. So everyone's independently created equations, and then you're summing up the a0 values for everyone's equation. And so for Pedersen's scheme, it's available and unpredictable. There are ways of biasing it, however, because there's no commitment scheme as such. Because you can say whether someone is in the qual set or not in the qual set, and that can help bias the output. And then these people added a commitment scheme, which removes the bias, or the possibility of bias. So recently, another blockchain, this is not Ethereum, but a crowd called DFINITY came up with a threshold relay scheme. And, no, that's no good. There should be a dot just there, which is not being displayed correctly. That dot meaning scalar multiplication. So to understand DFINITY's scheme, you've got to understand BLS signatures. And this is for the people who work within consensus here. This is a much abridged version of stuff that you can find in the R&D Slack channel. There's a massive presentation that Olivia presented on this. But essentially, so P is your public key, which is private key times the base point. And to calculate a signature in this scheme, you go private key times the hash of the message is the signature. And then really, what you really want to do is you want to find out if this equation holds. You know, essentially, so the base point times the signature, which is, you know, the public key times the hash. So you're saying, does the base point times the signature equal the public key times the hash? Because the public key times the hash, well, that public key was the generator times the private key, and then maybe you can say, well, generator times the private key times, or scalar multi times the hash, and then that comes back to that. So it seems really simple, and the only problem with this lovely simplification that I've done, this oversimplification, is that you can't actually do it because you're not allowed to do multiplication of two elliptic curve points. But at least nominally it gives you a bit of an idea of how it works. So really what's happening is you're on an elliptic curve, and so the public key was the generator times the private key gives you that public key. And the hash of the message is actually a point pushed to a point on the curve, and then you multiply it by the private key, and that gives you the signature. And then what you do is you do something called elliptic curve pairing, and that helps you map these points to a point on a different plane, on a different curve actually. And so this is actually using one of Blazer's slides, but I think it sort of covers it well. So rather than doing this multiplication, which you're not allowed to do, you do this other operation E, which is essentially pairing. And you're essentially saying, well, do all these signatures match? So this is how you're doing signature aggregation, and then using some fancy maths, which is summarised as magic, and it's, you know, not too far from it really. But you know, it obviously, if you're a mathematician, it's all good. Then you end up with this, and so you can do signature aggregation, which can be fast. So now that we've got the background material, how does the DFINITY scheme actually work? So you run the distributed key generation scheme for BLS for a threshold scheme. And then each participant ends up with a private key share. And then you generate your public key and you publish it, your public key share rather, and you publish it. And so you can get together a group public key by combining T of the public key shares. So then you've got your public key. And then to sign the value, what you're doing is you have the random number as the input, and then you sign it using your private key. And the signatures can be validated against the public key shares, and then you combine these signature pieces or signature shares into a group signature. And so the group signature is hashed, and that's the random output. So the thing to think about here is that the public key shares are public, and if you can accumulate from all of the different validators at least T of the signature shares, then you can assemble the next random number. So what that means is anyone can do it. There's no way you can block, because anyone has the power to create the next random number. So it seems pretty good, but it relies on, there's an availability problem here. And so there are some people who are down here on Ethereum research, Justin Drake, who's worked out that if 15% of the nodes are offline, then you can stall the actual algorithm. So 15% doesn't sound like a really big number to me. And you know, for Ethereum, where we're trying to, you know, like nuclear war happens and we're still cruising along, it doesn't really cut it. It does have the other properties, scalabilities. Well, it's still green, but it's definitely not quantum resistant. Okay, so I came up with a scheme. You know, everyone should come up with their own decentralized random number generation scheme. So this scheme actually works for an Ethereum blockchain, and in fact, if within certain properties, I think it's actually not a bad scheme. So choose a large prime number. Everyone registers as a participant, and so they generate an ephemeral key pair. So notice they're actually generating a new key pair that is just going to be used once. And they publish the public key to the blockchain. And then each participant has, their X value is calculated as their Ethereum address mod P. So you use the Ethereum address as a number. And then for all participants, you've got, they generate one of those random curves, one of those Shamir secret sharing style curves where you've got a set of coefficients and you've got a curve of order m. And you calculate the y values for each of the participants' x values. So for each of the other participants, you calculate the y value. And then you post the message digest of the y value for each of the participants' x values. And any participant that doesn't post a y value, the values, they drop out of the process and they get fined. And then all participants post an encrypted y value for each of the x values. So you're encrypting against the public key of each of the other participants. And then again, anyone who doesn't post gets fined. And then what you do is you post your decryption keys. And so you've got your public key there, you've posted encrypted values, and you've posted commitments to the values, and now you're posting your private key. So now everyone should be able to decrypt the values. And then, so anyone can now decrypt the values, and they can calculate the random value is the sum from 1 to n of the x equals 0 values, the y-intercept, mod p. So if m of the attackers collude, then they could decrypt the y values and they could choose which attacker should withhold their private key. So if you had a consortium of, say, 5 people, and that was m, then they could choose to not reveal, and I could, within the 5 of us, we could choose which combination of us weren't going to reveal, and in that way bias the output. So we can't change the output completely, but we can choose which of us don't reveal and hence bias the output. If you had n minus m plus 1 colluding attackers, then they could withhold their keys and in that way stop the algorithm. So that'd be like an availability problem. So hence you're likely to choose m to be about halfway, of half of the participants, so about 50%. So it's really saying it's good as long as you don't have more than 50% attackers, which is probably okay in some situations, but I think some people have talked, well, if you're in a casino, you want to be sure that everyone, you've got to assume everyone except for you is an attacker. So maybe for a casino this isn't good enough, but for most other applications maybe it is. So it's a leaderless scheme, which is good, and it withstands attacks up to m of n. So really it's about 50%. But its scalability is not too good because you've got to have 3 times n squared so communications, so that's quite a lot. So yeah, you're certainly missing out on the scalability, and I think the unbiased, maybe I should have had that in a darker green or brown, because if you've got enough colluding people, you could bias it. So just as I was coming out with my scheme, Justin Drake, who's one of the names that you've probably seen on a few of the other Ethereum research posts, he came up with a very similar scheme, but in some ways better. So his scheme can only be used with ECC, and so your private key is actually the y equals 0 value. So it's actually the y-intercept, x equals 0 value, so it's actually the y-intercept. And the public key is the commitment to the private key. And you calculate the coefficients by using an algorithm where the hash of the private key, and then you do sequential hashing to give you the other values. So it's all essentially based on the private key as your coefficients. And that should be mod P as well. And then, so each party publishes their public key, and then they publish their encrypted y values, values for each of the X values for each of the other parties, and then they publish their private key. And then invalid values can be challenged, just like my scheme, and then the output is the sum of the private keys. So it's actually a simpler scheme. There's less to be posted. So it's more an n squared scheme rather than 3n squared. So it's a better scheme. But it has pretty much the same properties. Yeah. So golly, I've talked about a lot of different schemes, and there's been a lot of rat holes of obscure maths and stuff. But I think different scenarios probably call for different schemes. And yeah, so I don't think you could just rush into saying, well, this one's the best for my scenario. I think you've got to look at each of the schemes in detail and work out what your scenario really entails before you go down the track of deploying something. Are there any questions? David?
When you look at newer consensus algorithms like Snowflake, Snowball, Avalanche, they need to choose a set of verifiers that change over time.
Mm-hmm.
Have you given any thought to the kind of random number generation, the properties of a random number generation algorithm that would be best used to select verifiers in consensus algorithms like that?
Well, look, I think the idea of doing RANDAO, maybe RANDAO with the VDF, I mean, it seems like a good initial approach because it's solving very similar things. So in Ethereum, you've got proof of stake validators, and you've also got, for the sharding, you need to work out the validators, and they use it for working out chains and stuff. So it sounds like a very similar scheme. Yeah. I think the DFINITY thing where you don't have that good availability, I think is a real problem for a blockchain system, because you can imagine you all have people who are trying to bring you down and stop you. The scheme that I've got and the Justin Drake, that one requires some sort of shared, knowledge, and I guess a lot of them do, but because even the RANDAO, you've got to put those commitments somewhere. What the latest commitment value is. So, yeah, that's my gut feel.
And that's the source of the scalability concerns, that shared knowledge.
I don't know that there are scalability concerns for the RANDAO one, because all you're really doing is just one entity is doing the operation, and it's a really simple operation that doesn't involve fancy mathematics in one place, but can be reproduced by everyone, and it's really simple. Are there any other questions? Okay. All right. Well, thank you everyone for coming along, and have a great day.